Hello, can you hear me? This is me, Gene. The reception is not really good here. There is some heavy magnetic activity around Mars today. Let me change the position. Hang on. Well, I hope this is much better right now. The idea of podcasting from outer space is cute, but maybe not very practical. Hello again, my name is Gene, a GeneUS programmer, and this is my channel, Crazy Algorithmics. Yes, I will emphasize the word crazy, just in case you haven't caught it. As you have probably guessed by now, I'm in a spaceship right now flying around Mars, at least in my imagination, and I'm sure you know from watching movies, of course, right now is a good time for us to find something strange on Mars, like an ancient artifact perhaps. And you are absolutely right, we did it. Let me get your attention to one of the monitors behind me. Our scanners discovered and recreated a map of a maze on Mars leading to an ancient artifact. And we'll be sending the rover to explore that maze and hopefully get the artifact. But that won't happen unless we can create an algorithm to process the map and find the path our rover should take. Okay, let's just put this crazy and hopefully at least slightly entertaining stuff aside for a moment and get real. But you see, I'm willing to travel all the way to Mars, at least virtually, just to get your attention to the topic of array traversal and recursion. So, let's get started. Nowadays, we are relying on a lot of images, whether we're talking about face recognition or analyzing satellite images to study climate change, possibility of wildfires, etc. We're not going into big topics of data science and machine learning today. We'll talk very basic stuff. Here's a two-dimensional array. I put zeros as placeholders, but it may have some numbers. We'll make each square a byte, which means it can hold numbers from 0 to 255. Now let's make our array three-dimensional by adding two more layers. And that's how the picture looks like under the hood. I'm talking basics, of course. The picture is nothing but a huge three-dimensional matrix which holds data for red, green, and blue colors. Perhaps you've seen something like RGB with numbers or hashtag with some letters and numbers used to set the color on the web page. Here I'm showing just two possible ways to tell that color is white, by the way. Numbers mean the intensity of each of those three base colors. The color comes out of combining the elements of the corresponding locations in all three layers. And of course 256 times 256 times 256, because we count in zeros as well, will give us almost 17 million colors each pixel can hold. Wow. Well, in data science, we may not care about how pretty the view from satellite is. These arrays can be used to transfer very valuable information about some features we need to study. Let's take a look at the map I got from our imaginary Mars scanner. Of course, this is the most simple map I could come up with. The dark is a corridor, light yellowish is the ground, and red is the chamber with an artifact. That's our goal. We will assume that everything outside of the boundaries of this array is a ground. For this exercise, we'll be starting in the upper left corner. If I put a grid layer over it, here's what we have. Of course, most likely the path in the maze will be wider than 1 pixel I'm showing here, but image recognition and normalization is far beyond the topic we have today, and we will only be working with one layer of this image matrix, which is two-dimensional array. I can now add the numbers to show how this will all fit together. For simplicity of my examples, I use 0 to indicate the ground, 1 to code the path, and 8 the goal, which is an artifact. I chose 8 for no particular reason. The goal of today's exercise is to traverse this array and to find the path to the goal. That's it. Of course, we need this path so we can send it to our Mars rover, also imaginary, and tell it where to go, but that will be topic of the next video. So, here's the array. The goal is to find the path from starting point to the goal and return the path as a string. For this exercise, I will assume, again, assumption, but I will assume that top of the map is north, bottom is south, and then we have east and west accordingly. Later, most likely, we'll change it, but for now, this will do. The recorded path will come back as a string of characters N, S, E, and W, indicating the direction of the movement, and we'll be using it later in another video to tell our rover where to go. Since I used C# in our last episode, today I will use Python. But since the code itself is very simple, most of my talk will be explaining the logic I am using, and at the end I will also give you an example in C#. Both of these examples you can find in my blog post on my site GeneUSprogrammer.com. The link is in the description. So, as beautiful as my little map is to human eye, the program sees it like this. I will be coding in Jupyter Notebook, and the first thing I will do is create our array. In Python, I will just create a list of lists, like so. My first approach would be to create a simplest working solution, even if that solution is just a brute force. Let's look at this map with numbers. I can imagine for a moment that it is me standing here, not the rover, and I have to find the path. They drop me underground through the hole in the upper left corner of the map, and I need to find the way. Standing in that spot, I will look north. Not good, it's a wall, a ground. South, that's another wall. West, the wall as well. So the only solution I have in this cell is to go east. I'll take a step and repeat all of the above, except I don't want to go west because that's where I came from, but computer doesn't know. As a human, I would put some kind of a mark there so I wouldn't step twice into the same spot. I will do the same in my code. That's so human. Oh well. So the approach I'll be using here is explore every possible direction using recursion. Let's program it. Here's a very simple function that will do the job. Let's take a look at what it is doing. First, we need to check for base cases. They are the cases that stop our recursion. First, I have to make sure that my coordinates are within boundaries of the array. After that, I will check if the value is 0, which is ground. In any of these cases, I will return an empty string because it means that this thread does not have a desired outcome. My next piece of code will check if I reach the goal, which is number 8. There is nothing magic about this number, just the one I chose for this puzzle. Okay, my next step is to mark this spot I'm standing in as visited. I can just put 0, and my base case above won't let me to go there for the second time. Remember though, I am modifying my array in place. I'm not taking extra space for additional arrays. This will save us a lot of space, but this will also make our life more interesting later. You'll see it soon. Now we have 4 recursive calls, one in each direction. If you look at the original parameters, direction by default is B, which means beginning. That was my idea. So each recursive call will receive my array, the same one I'm using, and modified new coordinates with new direction. Going north will get N, south S, etc. And the whole process repeats. Each recursive function call is stateless, so it has no knowledge about any previous functions. The only information it has is what you pass from outside. Keep it in mind. You have to treat recursive functions like it is just a chain of identical but totally separate functions. These are 4 functions we call from our first one. Let's pretend that the second square was the last one with a goal. These are return values. Recursive call north will return an empty string because we have a wall there. So is south and west. But when we move east, we see number 8, which is another base case. Since the direction argument for this call was E, the return string is E plus G and exclamation sign as we programmed. Now we are back to the original call since all 4 recursive calls return values. This if block will check which of those calls has a value, not an empty string, and it will return direction for this iteration, which was B, plus the result of the recursive call. And the path we are looking for would be BEG exclamation sign. Exclamation sign here means yay! That's an emotional response for humans because computer doesn't care. Of course, longer path will generate longer string. The recursion will go until it hits the base case. If I use my function to traverse this array, I will get an instant, very fast result. This assert is Python's way to verify the result. It will throw an exception if these are not equal. Also, as you can see, I'm using NumPy array here. NumPy is one of the most widely used libraries in Python. It is much faster than list of lists, and it is usually the method of choice when it comes to processing numeric data. As a full-stack developer, I like using object-oriented programming in my software, so my next step is to make a class out of my function. Here we go. The function itself did not change except I made it private. The main function though is just creating a NumPy array and verifying that the array is two-dimensional and it is an array indeed. Just some basic defensive programming. Everything else is the same. Here's the result of using new class with traverse function. It is identical to the first one. Awesome solution. The job is done, right? Wrong. We haven't solved anything, really. There are a couple of things here that can be devastating to our application, and the first one is our false assumption that we may only have one path to the goal. Remember, we are dealing with a maze, not just exercising in recursion. Here's another map. Let's say our scanner just discovered another path. It was under the mountain, so not as easily detectable, but we found it and created an image. How will our function process it? Any ideas? Here's the result of using modified array. It is exactly the same as the previous one. Why? The blue path is obviously shorter. Let's look at this spot in point X. The function makes 4 recursive calls here as it does everywhere else. We get 2 valid results from north and east direction. They both have values. However, our if block was set up to return the first value, which is not an empty string, and north is the first one in the sequence, which means the first one wins. Now we have to modify our function. All I need to do is replace this long if block with a code that selects the shortest path. Let me explain what I did here. This is a Pythonic shortcut to the process. If you work with C#, it has LINQ, which can do similar thing. If you are not familiar with Python, this expression is called list comprehension. It says basically loop through the list of elements and get the element if it is valid. In Python, I don't have to check if the element is null or none or is an empty string. You just write Pythonic way. If X, that means that X has a valid value. The return type is a list. It can be an empty list or a list with one or more elements. Again, here's a Pythonic way to check. If not valid path, which means the list has no elements, then return an empty string. None of the recursive function calls returned any value. Otherwise, select the minimum value from the list using the length as a key and add the shortest value to an existing path. Now, if I run the same code, I will get the perfect result. Yay! That's exactly what I needed. However, remember I told you that this blue path was under the rock. There was some magnetic interference, and the real path is not what you see now. Here's an updated map. Looks almost identical. There's a very small difference. Do you think my algorithm can handle it easy? Perhaps you've guessed it. If I'm asking this question, there must be a catch. It is indeed. When I run it, I get the same long result as I was getting before. It looks like the shortest path is not working. What happened? You may want to stop the video and try to figure it out if you don't see it yet. When algorithm gets to point A on the map, just because of the order of recursive calls, north direction goes first, and that is a longer path. When it gets to point B, the north takes precedence as well, and we go all the way up to point A. Since we already set the point A to 0, means visited, that's where it will stop, and it will see that blue path as a dead end. It will return to point B and get to the goal as usual. This did not happen before because in the previous map, long and short paths didn't intersect. They met at the goal. But in this map, they do intersect, and the first path will set value to 0 and make the second one impossible. When the algorithm gets to the goal and returns to point A, it won't take this blue path because it was already marked with zeros. And the only result we get is the longest path. That sucks. What can we do? Well, I have a genius idea. I feel like a generator of genius ideas today. Here's an updated code. I only added this line. Yes, I am marking the spot as visited with 0 as before, so the application won't step on its own tail. But I will clean it up and restore the path after all recursive calls are done and I'm coming back. Let's try. Voila! It works. My map is processed and I get a perfect result. But before I went to celebrate my achievement, I received another map. Here's a tiny maze not far from the first one. It happened to be positioned deeper on the ground, and it looks like this. Nothing spectacular. I sure can run it easily through my algorithm. Ta-da! It works. I get a perfect shortest path. However, look at the timing. This is not a joke or mistake. It took 13.5 seconds to run. I originally made this map the same size as the first one, but time was enormous, and by the way, it would return the same path, but it took much, much longer. I sure hope you saw the problem before I brought it up. Hope you're watching and thinking, what are you doing? Coming back, my algorithm is removing the marks of each point I visited. That means it will keep visiting every point again and again and again and again. Each function has 4 recursive calls. They will repeat traversal 4 times per function call. One of my favorite stories was about creator of a chess game. The king offered anything the creator wanted, and the humble math teacher asked 1 grain of wheat for the first square, 2 for the second, 4 for the third, and so on, double each time. For the first entire row, it only was 255 grains of wheat. Not too many. That's our 8-bit number, by the way. That's why my algorithm performed well with my first map. Not too many branching intersections. But the entire chessboard, if we double each cell 64 times and sum it up, we'll get, listen carefully, 18 quintillion, 446 quadrillion, 744 trillion, 73 billion, 709 million, 551,615. Try to say that on one breath. That's a lot of wheat, my friends. If you believe Wikipedia, it is about 2,000 times world wheat production we have today. And this is only a double. Our recursive calls are quadruple. Of course, those that don't have any intersection will return base cases really quick, but others will have another recursive calls. Do you see the problem now? It worked fine on the previous map because there was only a couple of possible ways, but here, with all these loops, application is freaking out. To solve this issue, I will try using another approach called memoization, another genius idea. I will add a dictionary to my Python class. You may be familiar with hash tables in other languages. It's the same, just a container which holds key value pairs. First, the container is empty. In my function, I will add another base case. I will compose the key using dash, otherwise coordinates 1, 12 will read the same as 11 too. So I need to specify, and if the value is found in the hash table, return it, end of story. I don't have to travel there again. If the key is not there, the code will run as usual up to this point. Since the only place where I may branch are intersections, I will only record the intersection, meaning there's another way to get to this point besides one I came from. These 4 recursive calls already found every possible solution out of this spot, and this means selected the shortest one. So if I add the value to the dictionary, I am sure it is the shortest one from this specific point. And if this is just a straight corridor, a pipe with no forks, I don't have to worry about adding it. The only way to get there is through another intersection. Now, if I run my algorithm using this smaller map, I get a successful result, and it took less than 1 millisecond. This is 15,590 times less than 13.5 seconds I had before. Do you think trading time for extra space is justifiable in this case? I think it is. And my large map only took 2.7 milliseconds. I can live with that. I think my crazy theory was pretty good. Unfortunately, it was just a theory. Let's look at another scenario. I will modify my latest map and put a target closer to the center, like this. I believe it should take less time and return a shorter path, right? Well, I was right about timing. Only 1.6 milliseconds. But what's up with the shortest path? Obviously, all my calculations were not very precise. It looks like the path is following this sequence of calls north, south, east. Memoization worked, but figuring out the shortest path did not. Okay, at this point I will stop the madness and change the approach completely. I did try different ways of marking each spot. I don't have to use zeros and ones only. I can use 2, for example, to indicate that I visited that spot already but have not finished with it yet. You can experiment with it on your own and come up with your own ideas if you like. In my new approach, I will look at all possible routes simultaneously. In my previous approach, I was going as far as possible before returning back. It is known as depth-first search. My next approach is called breadth-first search. Let me first explain what I will be doing. Here's that last array. I'm starting at coordinates 0, 0. First of all, I will explore every possible direction standing at this point. Not making a recursive calls like I used to do, just verifying if these points are valid. I will add each valid point to a list of children, so point 0, 0 will only have one child in this example, 0, 1. After that, I will call this function recursively and do the same with each child point on the list, so point 0, 1 will have two children. I will keep processing all points simultaneously. The first one who gets to the goal wins. I don't have to even compare the length of each path. I'm making one step at a time in every possible direction simultaneously, so I know when I reach the goal that will be the shortest path, or one of the shortest if several routes are available. Here's my new class. Let's walk through the code. First, you can see I took this long if statement out of the main function. It is checking if the spot is within boundaries of the array and if it is not equal to 0. You will see later that I will be checking each item on the list. I modified the method signature and now I am passing a list of points to check. Initially, the list only has one point, which is our starting point, but this will change later. Inside my function, there's a loop which will iterate over the items of the point list. These are base cases. If the point equals to 0, we simply skip the loop, or if it is a goal, we will return the result. I'm not checking the array boundaries here because that's what I did earlier when I was checking if the point is valid before adding it to the list of child points. We'll talk about it in a second. Next, I will mark this spot as visited by making it 0. And here's the most important change. My code is looking in every direction from each point to check if next point in that direction is valid to move into. I'm using that function I mentioned earlier. If the point is not 0, which means it's not the wall, and we did not mark it as visited before by setting it equal to 0, and it is within the boundaries of array, then it is open, and we can add it to the list of child points. That's it. We can do that for all points on the list. Now we can recursively call this function passing a list of child points as an argument. Here's another interesting scenario. Our function returns the result of recursive call, or it will return none if the list is empty. Either way, there's nothing happening after recursive call. Some languages support tail call optimization, which means there will be no extra stack used by recursive functions if they don't have any code after recursive call. When I was programming Prolog years ago, I knew it was tail call optimized. Of course, Prolog is entirely based on recursion. What that means, I could call recursion as many times as I wanted without ever running out of stack space. As far as I know, C# and Python are not tail call optimized, but F# is. You can read about this online if you're interested. And you may want to find out if the language you're working with supports tail call optimization. Now let's run some test cases. Here's the last array I tried to traverse using previous method and the result I got. With new breadth first traversal, so to speak, we can get much better result, and it looks like it is 4 times faster. Now let me throw a couple of curved balls. This array does not have a target. That means it will try to search all possible locations. And if my function was correct, once it gets to the point when there is no more child points, it should return none. Indeed, when I run the code, here's the result. And another one just for fun. There is no maze at all. We have an open square hole with central pillar, perhaps for support or something, and the target is in the farthest opposite corner. Let's see what happens. As you imagine, every path will take the same length except the one that runs into the central pillar. What do you think will happen? Here's the result. All the way south, then all the way east. Why? Because our sequence of checking child points is north, south, east, west. Therefore, the way south, then east wins. And in south and east competition, south will always be at least one step ahead of east. You may try changing the sequence in the code and see what happens. I think this should be enough craziness for today. But this is not the end. I don't write software just for the sake of writing software. So traversing algorithm is not my goal. I need to solve a practical challenge with my code. I cannot guarantee that my code will ever be used by NASA for their trip to Mars, but hopefully I can make it a little bit more practical and little more interesting than it is now. So here's a couple of challenges for you to work on your own if you want. In fact, I'll give you 3. And don't worry, they're very simple, even though I hope they may get this algorithm a little bit closer to reality. Here's one. I'm assuming that the directions north, south, east, and west are valid on Mars and are easily detected by the rover. What if the maze is located in some kind of magnetic rock and all directional equipment is dysfunctional? So instead of relying on the directions from northwest corner of my map, I want to make a coordinate system with 0, 0 in the lower left corner. Then the entrance point may not be 0, 0 as it was with array. It will be something else like x, y coordinates. In my example I used here, it will be 120. Are you ready for some refactoring? The other one comes out of my false assumption that our equipment detected entire map of the maze. What if there are additional passages? Or, for example, we can make the entrance point 0, 0 regardless where we go underground. That means negative values of x and y are possible, which was not an issue with traversing the algorithm. Besides, the rover may have to create the map of a known territory on the fly. Finally, I started exercise with a single level maze. What if it has 2 or 3? Now we have to parse a three-dimensional matrix, not a flat array. If you look at this map, I used red, green, and blue colors to represent different levels. At these points of intersection, the rover can take either level in any valid direction, and this three-level intersection can be used to take any of 3 levels. All transitions are bidirectional, meaning you can travel either way. As far as my next step for the next video, I have some ideas to elaborate on. For example, I'm assuming here that all steps the rover is taking are equally easy. What if one path has level of difficulty equal to 1 and the other one equal to 10? Or here's another good idea. One path to lower level is bidirectional and the other one is only leading down but not up. You can drop in but never get out. You may be already guessing where I'm going with that, but I'll talk about it another time. Here's a C# code I promised. It looks almost identical except I have to specify each variable while Python makes the syntax shorter. I'm using a list of value tuples here and unpacking the tuple in C# way, but the logic is the same. That's it for today. Thanks for watching, and we'll have another crazy talk next time.